We're going to continue talking about reports here. What are the types of reports that are available? Calculated data. And let's say we're not going to do the correction. We're just going to do it at the 28 inches that it was actually measured at. And here you can see lift LV, the actual corrected CFM to 28 inches. The valve area. This is the geometric area of the valve opening. And you can see it's increasing here at low lift, but then you get up to a certain point, it tops out, and that is because the throat area is now the limiting factor, not the curtain area. And then it shows you CFM per square inch. Here is the actual flow area. And what this is, well, let me talk about flow coefficient first. The flow coefficient is how efficiently does the head flow for the amount of valve area available. For example, here you can see we've got very good flow, much higher flow here than we do down here. But because it's such a much smaller flow area, or valve area, I should say, the valve flow area, it's actually more efficiently flowing down here at low lift than it is up at high lift. But you can see when the area tops out here, when the flow goes up a little bit, even though the area is not increasing, it is now considered more efficient. Typically, you're going to get your lowest flow coefficient at close to an L over D of 0.25. But it just to give you an idea, this is an idea how efficiently a valve flows. Now here, if you look on the exhaust side, and this is true typically of exhaust, exhausts are flow more efficiently. You can see we're getting up 0.9 almost on the top end here. So exhaust valves, and this is what you look at to see how good are your heads flowing. It is possible to get a number over the number 1. I'll explain some here real quick, but let's just make a note. We're at 0.663 here, 0.897 here. I'm going to back out. I'm going to go into preferences, and let's see, general operation, definitions. What am I looking? Here it is right here. Average flow coefficient is based on either the valve diameter or the throat diameter. And here's another one. Here's a use seat angle to calculate valve area. We're going to say yes. We're going to back up. And now if you're going to go into your report, you can see these flow coefficients have increased because now we're taking a lot more information into account for what is the true flow area. And I'll show you that in a second out in the book here. Here I'm on page 68 in the manual, and it shows you some detail about the valve diameter or the valve seat angle and stuff. And here is a nice little graph. It's from our old DOS version, but the calculations are still the same, showing you the actual area, how the area available for flow changes with lift. If you just use a simple outside diameter of the valve, you can see I have a lot more flow area here than if you use the seat angle. And this one here, I believe, has a 30-degree seat angle, and this one here uses a 45-degree seat angle. And you can see there is some differences here. The larger the flow area for the same amount of flow, the less efficient it is. But if you want to get detailed here, and if you don't understand what this stuff is, just keep it at the default so that it was set up for before. But if you want to get into detail, like some Formula One guys, we can do it for you. And that's what I wanted to illustrate right here. So we're back in our port flow analyzer here. And some other things you can do is maybe you don't want to report all cylinders. Maybe you just want to average out everything for the head. And here it is. It's telling you it's an average of 4 points, each one of these. You get your intake and exhaust, percent intake to exhaust, and again, your flow areas and stuff. A couple other things here, and this is all covered in the book, so you can go to the book. Like I was pulling pages out. Um, the valve area. This is the geometric area. Now considering seat angle and a whole bunch of things. The CFM per square inch of area, and this has probably gone up because the areas are now smaller, calculated more precisely than they were before. The flow area here is a little bit kind of a complicated number to understand. It's related to flow coefficient. But what it is if you could flow this much CFM through an idealized orifice with a smooth entry and exhaust, this is how big that orifice would have to be. Or to get this much CFM at this test pressure, you would have an idealized hole of this amount of square inches. And you say, why do we talk about this? Because this makes for a nice way of comparing heads or lifts at independent of the pressure drop, independent of a lot of things. This is what the effective opening is if you can flow this much CFM at that test pressure. And you can see it goes up. As CFM goes up, it constantly goes up. The efficiency might change over here, but the flow area keeps going up as CFM goes up. Now, if you went and changed this, we've got 2.248. If we change this and now correct to 25 inches, our flow has dropped, but our flow area has stayed the same. And that is what is so nice about flow area. It is independent of so many things. Flow coefficient did not change either. It is still just as efficient, even though we're correcting now to 25 inches instead of 28, and the actual flow dropped off. Okay, valve velocity. This is the velocity in feet per second of the air going through this area right here, the valve area, the curtain area when it's down low, the throat area when you get up high, at high lift. This is the port velocity. This is the velocity of the air going through the port. Here's a port area up here in square inches. This is what you put in the head specs. And you can see this velocity typically will fall down, drop down. It's somewhat related to flow coefficient. At very low lifts, it's pretty high because it's a very small valve area, because the valve is it's the curtain area. That's the restricting factor. And then again, it falls to a minimum here at roughly elevated at 0.25, and then starts going up again. But the port velocity just keeps going up. That is because it's based on flowing this much air through this size hole. Some other options you got with report types. Let's say you just want to do the first cylinder, number one cylinder only. Then you got that. Or let's say you wanted to pick. And let's say I want to do cylinder 1 and 3. 1, comma, 3. Okay? Put a comma to separate the cylinders. And there you have cylinder 1 and cylinder 3. There's some other report types we can do. Let's say we got it set up for doing the average of the head, and we're going to compare CFM between a couple different heads. Choose this one. You make the report for comparing heads, the corrected CFM versus lift. And what it will do then is open up the library and say, what head do you want to compare this to? Compare the Brodix head to. And let's say we just pick the Chevy 18-degree head. And there you have a nice comparison between the two. The lift, the CFM at 25 inches, and then the lift on this one, the CFM difference, and the percent difference. So you have a nice report comparing two different heads. Again, it says tested at 28 for both. Here is the heads. And that it was you corrected the data at 25 inches. Now, I'm pretty sure if you do corrected this comparison stuff, I think you got to be careful. You can't pick different cylinders or just the first. You might be able to do the first cylinders also. but there are some limitations on what you can do. What else we got here? Obviously, it's going to be same thing, valve area, peak velocity corrected CFM at L over D instead of inches and stuff. Um, a cylinder-cylinder comparison, we can do this. Here's what this report looks like. So there's a lot of different options for different types of reports here, and picking which cylinders you want to do and doing comparison between different heads and such. So that's one way to analyze data.